Okay, let's do an example of a spring problem. Suppose a force of 250 newtons stretches a spring 30 centimeters. How much work is done in stretching the spring from 20 centimeters to 50 centimeters? Now, one thing I don't think I made sufficiently clear in the last video. If you take a spring with no weight on it, we're going to say that it has been stretched 0 centimeters. That is its natural relaxed length. If you put a weight on it of 250 newtons, it stretches it from 0 down to another length of 30 centimeters. So that's the 30 centimeters. It's not the overall length of the spring. It is the amount of force is directly related to how far beyond its natural relaxed state the spring has gone. Anyway, so what do we know? We know that this force, the force is K times X. In this case, 250 newtons is K times 30 centimeters. I'm going to use meters, 0.3 meters. So K is 250 divided by 0.3, which is 250 divided by 0.3 is 83 and a third, 833 and a third. What are they? It's going to be newtons per meter. A newton is a kilogram meter per second squared, so it's just a kilogram per second. Doesn't matter. It's a constant. So, how much work is done stretching the spring from 20 to 50? Well, the work is going to be the integral from 0.2 meters to 0.5 meters of 833 and a third x dx. Not so terrible. What have we got? We've got 833 and a third x squared over 2 evaluated from 0.2 to 0.5, which is going to be 833 and a third. What is this? Oh, let's move the 1/2 out front. 830, no, and a third, divided by 2, and let's see. 0.5 squared is 0.25 minus 0.2 squared is 0.04. So that is 833 and a third times 0.21 over 2. Blah. What is this? There's the 833 and a third times 0.21 equals, divided by 2 is 87.5 joules. 87.5 joules, which if I remember correctly is a whole lot less work than carrying a fire hose to the top of a ladder in a problem I made up entirely on my own. Now, in this case, we were told that 250 newtons stretches at a certain distance, and that enabled us to calculate the K. It could be that someone would have said, oh, it takes 875 joules to stretch it from 2 to 5, from 0.2 to 0.5, in which case you would have known that 87.5 joules was enough to go from 0.2 to 0.5 of kx dx. So that is kx squared over 2 from 0.2 to 0.5, and 87.5 is some constant times, what is this, 0.25 minus 0.04 over 2, and we could have worked this out. This is what, k times 0.21 halves, so 87.5 times 2 divided by 0.21 ought to be 87.5 times 2 equals divided by 0.21. There's the 833.3333. Right. 833 and a third. So there's two different ways that these spring problems are sometimes given to you. They either tell you how far it stretches when you put a single weight on it, or they tell you how much work it takes to do something with a spring. And then once you get that spring constant, you can figure out anything you want. Like if you put a 30 kilogram weight on this, let's say 3 kilograms. If we put a 3 kilogram weight on this spring, there's the spring, there's the relaxed spring, here is the spring with a 3 kilogram weight on it. What is 3 kilograms? 3 kilograms is 3 times 9.8, 29.4. 29.4 newtons, and the distance it's going to stretch of x is directly proportional to that. We know that 29.4 is 833 and a third times x. So x is 29.4 over 833 and a third. 29.4 divided by 833.3, which is 0.035. 0.035 meters, also known as 3.5 centimeters. So this is a pretty burly spring if putting a 3 kilogram mass on it only stretches it 3.5 centimeters.